Good morning. So today we are going to discuss about the unit 1, that is analytical function. In that topic 1, that is analytical function, we are going to discuss. So first of all we are going to see about the neighborhood points. So how will you neighborhood points means if you consider Z0 as a center point and the nearby points are, we can say it is a neighborhood point. For example, Z0 is a center point, Z1, Z2, Z10, etc. We can say it is a neighborhood points. So how will you represent the neighborhood points means that is modulus of Z minus Z0 less than epsilon. The elements we can say the elements within the distance of modulus Z minus Z0 less than epsilon, we can say it is a neighborhood points. If deleted neighborhood points means Z0 will be absent, so it is represented as 0 less than modulus Z minus Z0 less than epsilon. So next we are going to discuss about the definition of the differentiability. So differentiability definition is nothing but limit z tends to z0 f of z minus f of z0 by z minus z0 equal to f dash of z0. So we can say it is a differentiable. And what is mean by analytical function? So a complex function is a f of z is said to be analytic at a point z0 if f of z is differentiable not only for z0 also in some neighborhood of z0. Okay. So analytical function, we can say that is the function is differentiable at all points. So we can say it is an analytical function. So next, it is an important theorem we are going to discuss based on the analytical function, that is Cauchy-Riemann equation. So Cauchy-Riemann equation, we can state it is a necessary condition for the complex function is differentiable, or we can say it is a Cauchy-Riemann equation for Cartesian form. So now we are going to discuss further about the Cartesian form. Now f of z is differentiable at z0. So limit, what is the differentiable definition? Limit z tends to z0 f of z minus f of z0 by z minus z0 equal to f dash of z0 exists. So now we are going to consider the two axes. So normally you have the x-axis and y-axis. So x-axis is taken as a real axis while y-axis is taken as an imaginary axis. So let us take that z approaches to z0 traveling along the parallel to the real axis. So parallel to the real axis means z equal to z0 plus h. So where h is real and tends to 0. So now we are going to apply this condition in the definition of the differentiability. So you will get f dash of z equal to limit h tends to 0 f of z0 plus h minus f of z0 by h. So what is z x plus iy? So now we are going to write z0 can be written as x0 plus iy0, and you can write in the form of a function. What is f of z? U plus iv. So you can express in the form of the u function. So you can write in the form of an in terms of u function and as well as a v function, and differentiability definition, and finally we will get a answer as ux plus ivx. So take it as equation 1. Then now we are consider z not traveling along parallel to the y axis. Then z equal to z plus ik, where k is real and tends to 0. So similarly same formula are going to apply. There is a limit k tends to 0 f of z0 plus ik minus f of z0 by ik. So what is z0? x0 plus iy0. So you can apply the complex function u plus iv. So instead of f of z0 plus ik can be written as u of x0 comma y0 plus k, you can write it. So you can expand the above equation, and if you simplify that you can apply the definition of the differentiability. Finally you can write I ux plus vy, uy plus I uy plus vy. This is your equation 2. So now you can take the equation 1 and 2. What is equation 1? Ux plus I vx. What is equation 2? Minus I uy plus vy. You can compare real part. So what is real part? Ux equal to vy. What is imaginary part? uy equal to minus vx. So this is said to be an Cauchy-Riemann equation. So we can see the Cauchy-Riemann also here. So, and also simple problem I have explained here based on the analytical function, how you can find whether it is an analytical or not. So when will we test it is an analytic? Based on the CR equation. If the function satisfies CR equation, then you can say it is an analytical function. F of z equal to z cube, z equal to x plus iy. So you can apply now. How will you write z x plus iy? If you substitute x plus iy the whole cube, and you can expand by a plus b the whole cube. So if you write a plus b the whole cube by expansion, and from that you can split the u value and as well as the v value. So u value is x cube minus 3x y square plus I 3x y square y minus y cube. So now we can take u as the real part and v as imaginary part. So our work is to check whether it is satisfy the CR equation. What is CR equation? Ux equal to Vy, Uy equal to minus Vx. No. So first of all you are going to differentiate with respect to x. So if you differentiate u with respect to x means, what is x cube differentiation? 3x square minus, so you can take y square as constant, only x if you differentiate you will get 3, if you differentiate x you will get 1, so minus 3y square you will get. Similarly uy, we can differentiate with respect to y, so you will get minus 3x y. Okay, so if you multiply you will get 3x into 2y, so 3 2s are 6, so minus 6xy. Similarly you can find the value for vx and as well as the vy, so it satisfies all the condition, but CR equation you have to check it, no. So ux equal to vy, so compare the equation. What is ux? 3x square minus 3y square. What is vy? 3x square minus 3y square, same, no. So first equation satisfied. So if you see the second equation, uy minus 6xy, and if you notice the vx, that is nothing but minus plus 6y, so that is also satisfies the condition. And also with very important problem we are going to see, and it's a theorem based problem also. So f of z is a function analytical in a region D. Its real part is constant, imaginary part is constant, and modulus of f of z is constant. If you assume these things, based on the assumption, finally you have to prove the f of z is constant. So we can see 3 cases here. So first case we have to assume real part constant, then you have to prove that f of z is constant. So let us take f of z equal to u plus iv. So we can consider real part now. Which is the real part? U is the real part, everyone know. That is equal to constant. Take it as k. If you differentiate f dash of z, that is equal to ux plus ivx. So CR equation you applied means ux plus I into minus uy. You will get it. So k is constant now. If you differentiate k, constant differentiator will become 0. So all the thing will become 0. F of z equal to 0. F dash of z equal to 0. But if you integrate, integration of 0 will become constant. So f of z equal to constant. So you have proved. Next we can go to case 2. If the imaginary part is constant, what happened? Let us see. F of z equal to u plus iv already taken. Which is the real part of u? F of z equal to u plus iv. U is real part, we have discussed, but v is our imaginary part, no. So we take v equal to k. Same procedure you have to do. F dash equal to ux plus I vx, and you can change using the CR equation as u vy plus I vx. Then finally it will become also 0, and if again integrate, same procedure it will be applied. Now we are going to case 3. F of z is a function analytical in a region D. It's a modulus of f of z is constant, then f of z is constant. So for this slide simplification is there. So f of z equal to u plus iv. So if you take a modulus square, what is the absolute value of u plus iv? U square plus v square. That is a constant. Now if we differentiate with respect to x and as well as with respect to y also. If you differentiate with respect to x means you will get about 2u ux plus 2v vx equal to 0. If you take 2 as common, it will go that side, so you will get u ux plus v vx equal to 0. Then you have to move on to the CR equation, and again if you apply the with respect to y, differentiate with respect to y, we will get the same thing, u uy plus v y. Second value will become as u, that is u y, then